Welcome to this explainer. Today we're doing something really cool. We're decoding the spectacular transformation of scrap metal through two incredibly fascinating lenses, thermodynamics and energy economics. We so often look at steel as just this heavy, static material, but the process of actually creating it is a masterclass in extreme physics and razor-thin profit margins. So think about it for a second. How exactly do we take rusty, jagged, just totally chaotic scrap metal from a junkyard and turn it into the highly calibrated, earthquake-proof structures holding up the skyscrapers around us? Well, it definitely doesn't happen by accident. It's a massive exercise in what we're going to call thermodynamic value addition. Okay, let's dive right into this structural metamorphosis. Look at this glowing red-hot steel. This is that magical moment where extreme heat basically acts as the ultimate reset button for old, discarded metal. We are literally breaking down matter to rebuild it stronger. Section 1. EAF, Thermodynamic Value Addition. All right, let's establish a really crucial vocabulary anchor here, the EAF, or electric arc furnace. Now, this isn't your granddad's 19th century coal-burning blast furnace. No way. The EAF is a refractory-lined vessel that uses huge carbon electrodes to literally zap steel scrap with insane amounts of electrical current. It melts it all down at extreme temperatures, making it the primary vessel for all this thermodynamic value addition. And you've got to notice the chemical separation happening here. When you blast raw electrical power into that scrap, it forms a liquid pool. All the oxidized impurities, the rust, the dirt, all that junk, they float right to the top as this highly corrosive liquid we call slag. Meanwhile, sitting perfectly underneath that slag is a totally clean, purified bath of liquid steel ready to go. Section 2. The continuous casting bottleneck. So, as we move from a glowing pool of liquid metal into a continuous flow, the absolute most crucial thing to understand is the billet. As the liquid steel pours out of the caster, it solidifies into this long, semi-finished rectangular block. This billet acts as the fundamental building block that transitions our steel from the melting phase straight into the shaping phase. Now let's watch how this actually builds through the rolling mill stands. It's wild. The billet, which is heated to over 1100 degrees Celsius, goes through three distinct stages. You've got the primary mills doing the rough squeezing, the intermediate mills refining those dimensions into a long rod, and finally, the finishing mills. Those are what press the iconic rib patterns right into the steel, the exact patterns that allow rebar to grip onto concrete. But what's truly mind-blowing about this process is the sheer tension of the continuous flow. We're talking about a glowing river of steel moving at incredibly high speeds. And get this, every single one of those rolling stands has to spin at the exact, precise mathematical speed. If just one downstream stand spins even a fraction too slow, boom, this whole river of hot metal bottlenecks, instantly creating a catastrophic pileup right there on the factory floor. Section 3. Quenching, the TMT advantage. Okay, so assuming the mill runs perfectly and the shape is totally finalized, we pivot to the really advanced metallurgy. This brings us to TMT, which stands for thermomechanically treated steel. You've probably seen this acronym plastered on construction sites everywhere. It's a highly specific manufacturing process that boosts the rebar's strength, not by mixing in different metals, but through rapid, masterfully controlled cooling. The absolute secret sauce here is the quenching phase, often using something called the Thermex process. Basically, as this red-hot bar exits the rolling mill, it gets blasted with high-pressure water jets. This sudden, violent cooling instantly freezes the exterior. But because the bar is so thick, the inner core stays blazing hot. So the heat from that core naturally radiates outward, self-tempering the entire bar. It's brilliant. And the result? A revolutionary dual-phase structure. On the outside, you get this hard, martensitic outer layer that gives the steel immense tensile strength and toughness. But on the inside, you have a soft, ferrite pearlite core that keeps the bar highly flexible and ductile. This exact dual-phase structure, this combination of hard and soft, is the literal reason a building's rebar can bend and stretch during a massive earthquake without snapping in half. Section 4. The energy efficiency moat. Now, actually making this incredible steel is really only half the story. We've got to shift our perspective to the harsh underlying economics of the business. 50 to 80 kilowatt hours. That is the massive amount of energy required to hot roll just one single ton of steel. When you're pumping out millions of tons, the real competitive advantage, your economic moat, isn't actually found in the steel itself. It's entirely in your kilowatt-hour management. Because the reality is, millions of dollars in profit are won or lost right here. Think about this. Reheating furnaces alone account for 40 to 60% of a rolling mill's total energy consumption. Any mill that actually wants to survive in today's cutthroat market absolutely must figure out how to optimize this massive thermal requirement. And when you look at the melting phase, the scale of lost energy is just staggering. Look at this. 70% of the energy losses in electric arc furnace steelmaking simply escape through hot off gases if they aren't managed properly. I mean, that is literally money just vanishing into thin air. But, this is exactly where engineering strikes back. Modern efficiency solutions are totally transforming this industry. Waste heat recovery systems can actually capture that escaping gas with 60 to 70% thermal efficiency. You've got variable frequency drives on the rolling mills that drastically reduce motor energy, like by 20 to 50%. Siemens has even developed regenerative braking for the mills that recovers up to 30% of the energy and feeds it right back to the grid. Plants deploying these advanced digital and mechanical systems, they inherently win the market because they drastically lower their baseline production costs. Section 5. The Mill Test Certificate. All right, we need to anchor all of this thermodynamic effort back to reality, specifically through the eyes of a structural engineer or a senior quantity surveyor. Before any of this rebar even touches a construction site, it has to prove its yield strength. Now, yield strength is the critical stress threshold where the steel actually begins to deform permanently. It won't snap yet, but it will warp. That makes it the absolute most vital metric to ensure a skyscraper doesn't just lean or collapse under its own massive weight. So every single bundle of TMT steel comes with a mill test certificate. Think of it as the steel's college diploma. It demands precise validation of that yield strength, exact tensile strength, and a super strict spectrometer chemical analysis. Specifically, it has to prove the steel has low sulfur and phosphorus, which, as we mentioned earlier, is absolutely required to maintain that crucial ductility. Because here is the brutal, unforgiving truth of the steel industry. If a batch fails that chemical analysis, or if it falls short on yield strength by even a tiny margin, all of that effort, all that energy, the melting, the rolling, the quenching, all that thermodynamic value addition is instantly reduced right back to trash. It's scrapped. But that strict engineering rigor, that guarantees that only perfectly balanced dual-phase metal makes it to the foundation of your home or office. So, I'm going to leave you with this provocative thought. We usually think of steelmaking purely as an exercise in metalworking, right? But as we've just seen, it's actually a masterclass in energy economics. If energy recovery is the true moat of modern manufacturing, what other heavy industries out there are secretly just giant exercises in thermodynamic management? It really kind of shifts how you view the whole industrial world, doesn't it? Now, if you want to geek out and dive deeper into the exact mathematical formulas driving this massive industry, from rolling stand synchronization to EAF thermal efficiency, I highly recommend searching for the AIST technical papers and checking out the engineering toolbox for steel rolling. They are the absolute gold standard for this kind of rigorous analysis. Anyway, thanks so much for joining me on this explainer, and keep questioning how the world is built around you.